So where did things go? What's the fix to this? The unfolding, it's this unfolding, which is almost right. Let me move it here. So when we do this unfolding, it's almost right. So we have this sum. You see what's going on is that really the mistake, it's not that subtle. It's pretty obvious after the fact, I suppose. But the blatant mistake, where was it? It was right, this fixed constant thing, that there should be a W, the number of roots of unity should be here. So that I said, yeah, it's just a constant, it's not a big deal. Well, that constant came back to bite me because I was sloppy with it. So the reason there's a constant is that when you look at this sum, what we're really doing is we're looking at these closed geodesics, but we're just taking one period of that closed geodesic, right? This Q has an automorphism group. There's a stabilizer. And so the classes have a stabilizer. So it's really gamma mod, I'm going to call this gamma H. Gamma H is the stabilizer of that particular Q. In fact, gamma H is exactly the group generated by M. Gamma H is the group generated by M. I'm just going to say this very quickly, just to record it, and then we move on to Hecke operators, just to get it right. So the Q is corresponds to the closed geodesic. Of course, we only want to take one period, but when we do this unfolding, in order to unfold, since this action, the gamma action, has now not a finite stabilizer, but an infinite stabilizer, when we unfold, we have to write this gamma as a gamma mod gamma H, and then a sum over, I don't know what to call it, H in gamma H. And then the composition, whatever we have here, is going to be a Q composed with gamma, composed with H. So then when we unfold this sum, we indeed get a sum over Q in gamma mod gamma infinity. But then this sum, this action is a sum over H in gamma H and an integral from 0 to LD. But the way that this acts, okay, I'm going very quickly, but the way that this acts is to translate, instead of going from 0 to LD, this becomes, the way that this acts, the way that each of these H's, I mean, I'm not putting in what the dependence on H is. This is equal to a sum over the integers of an integral, this is a sum over all integers, of an integral from, let's call it n minus 1 L to n L of this function. And so we didn't have this sum. We didn't have this infinite sum. So we had an integral from 0 to LD, and of course that depends on D. But actually it should have been a total integral over R of that same function. So it should have been an integral over the whole geodesic. Okay, and that's what I sort of mumbled here at the very end, that it should have been an integral over the whole geodesic of this function, and that function, when as s goes to 1, goes to a constant pi over 2. Okay, so that's the little fix there. Okay, just to have that down on paper. Let me skip over here and let's talk about Hecke operators. So before Hecke operators, we need a space for the Hecke operators to act on. So before that, just a quick little crash course in modular forms. So we had been talking about the hyperbolic Laplacian, y squared times 2 derivatives in x plus 2 derivatives in y, acting on L2 of some fundamental domain, which is some region in the upper half plane, or automorphic functions more generally. There is another natural differential operator, which is the Cauchy-Riemann equation, right? Derivative of the first, derivative of the first thing with respect to y minus derivative of the second thing with respect to x. the Cauchy Riemann operator. And if f from the upper half plane, let's say to C, is an eigenfunction, well, eigenfunction with eigenvalue 0 is killed by Cauchy Riemann, of course, if and only if f is holomorphic. This is just a long-winded way of saying, instead of studying eigenfunctions of the Laplace operator, we're going to switch to studying holomorphic functions on the upper half plane, and not just any holomorphic functions. We want them to be modular. Want f to be modular.
So eigenfunctions of Laplacian gives us like the non-holomorphic Eisenstein series, and then eigenfunctions of the Cauchy Riemann operator gives us the usual Eisenstein series.
Exactly, and not just eigenfunctions with some eigenvalue, but eigenfunctions of eigenvalue 0. Okay. In other words, null functions.
Okay. But the non-holomorphic Eisenstein series they have eigenvalue s times s minus 1.
Exactly.
Okay.
Exactly. So we want S to be modular with respect to some group. Well, of course, we'll take our group in the baby case to be SL2Z. So what does modular mean? Of weight K. Of weight K, that means, this is a definition. F is modular. F is modular if for all gamma in SL2Z, let's write that as ABCD, and of course for all Z and Z, or Z in the upper half plane, F of gamma Z, the usual fractional linear transformation, is CZ plus D, this CZ plus D to the K times F of Z. So this is this co-boundary, if you like. Okay, so F is modular.
Like in the differential form sense.
Yeah.
Okay.
Yeah. So if we call this thing J gamma K of Z,
right. Okay.
Then
okay.
Yeah. Then J of gamma 1 gamma 2 is J of gamma 1 at gamma 2 Z times J of gamma 2 Z. Something like this. Should I make that a little exercise? Exercise. J of gamma 1 gamma 2 of Z. Let's see, it should be something like J of gamma 1 gamma. It's like a differential, it's like a chain rule.
Yeah.
Exactly. Gamma J gamma 2 of Z. Okay, so this is modularity. Now we want the space of modular forms. So let M K be, and it is a space because if you add two things that scale like this, and if you multiply something that scales like this by a constant, you still get something that scales like this. So this is the space of F from H to C, so that it's modular, holomorphic, so holomorphic, satisfies this condition. Now notice it's not absolute value because we want it to be holomorphic, and I have to fill in a couple of things about what's going on there, which I'll explain in a second. So given that it has this modularity, in particular, if I take gamma to be my favorite translation vector, that says that f of z plus 1 has to be, well, c is 0 and d is 1, 1 to any power is 1, I get f of z. And so f will have a Fourier expansion, f of x plus iy will have a Fourier expansion, sum over all natural numbers, all integers, I gave it away, some coefficient, af of n depending on y, e to the 2 pi I, and x. Now, but it has to be holomorphic. So if we apply Cauchy Riemann equations imply that this function of y gives a differential operator, now a first order differential operator. With the Laplacian, we had a second order differential operator, which was solved by these K-Bessel functions. Now we just have Cauchy Riemann equations, slightly simpler setting. This is going to be some constant times e to the minus 2 pi n y, which of course we could put these two together to say this is a sum over n in Z some coefficients AF of n, Q to the n, where Q is e to the 2 pi I Z. And we can think of this transformation as a chart at infinity. Chart at infinity. So we have our sort of standard fundamental domain. We can take a chart around any point. We want to make this into a compact Riemann surface. So around any point, well, it's not quite a surface, but an overfold, we have some cone points. Around any interior point, we have sort of the regular chart. What about the point at infinity? How do we take a chart there? Well, it's exactly this map. If we send Z to e to the 2 pi I Z, which is automatically invariant under this invariant translation, then Q, well, what happens to Z? So the absolute value of this, the absolute value of Q is e to the minus 2 pi n, 2 pi y. And so this is always less than 1. So this sends the upper half plane to the disk, but it sends infinity, unlike the, it's not something that sends boundary to boundary. It sends infinity as y goes to infinity, as y goes to infinity, absolute value of Q goes to 0. So the point at infinity goes to the central point. And that's why we have a chart around it. And it's invariant under Z goes to Z plus 1. So it's invariant under rotation. So it's a full disk. Okay, so this gives us our chart at infinity. And what we want is, of course, this extra condition is we want it holomorphic, not just in the interior, but and holomorphic at infinity. And in general, we'll want this holomorphicity at all cusps. What we really mean here, I mean, this is a fancy way of saying we don't want F to blow up.
Do you require F to be holomorphic at points on the boundary that are not cusps? Well, I guess we're only looking at fundamental domain. Never mind.
We will.
Okay, there's no boundary except okay.
Yes.
Okay, I see it. Okay.
So now you're asking about modular forms on thin groups, where you could have entire continuum of boundary touching a fixed fundamental domain. Yeah. So this holomorphicity at infinity just means it's equivalent to, as we'll see in a second, or maybe we see immediately, that F remains bounded. F does not blow up, because if we had, in other words, this sum had better not be a Laurent series in Q. It had better be a power series in Q. So this sum, what we need is that AF of n needs to be 0 for all n negative. Okay, otherwise we'll have some Laurent, so not a Laurent series, but just good old power series. Because the absolute value, if Q is less than 1, and now we're taking Q to a negative power. So as y goes to infinity, this would blow up if we had any negative n's participating. Okay. So that's this holomorphicity, which is equivalent to boundedness. Fine, that's the space of modular forms. This space is non-empty. So exercise. So now we'll introduce the holomorphic exercise / definition. The holomorphic Eisenstein series. Of weight K is defined EK of Z. So there's no S anymore. K has replaced the role of S. Is sum. There's a difference of opinion about how to do this. I'll say a sum over coprime C and D to make it look just like our other one. There's no y to the s because that's not holomorphic, but we divide by not absolute value of CZ plus D squared or to the 2s, but so no absolute values because we want it to be holomorphic, but just this to the K. I will use K. Some people use 2K. I like weight K, and K should be 4 or 6 or whatever. Right. So this is a holomorphic Eisenstein. It is a holomorphic function. Well, first of all, does it converge? So need K to be greater than 2 for this to converge. And since we want K to be an integer, K should be, i.e., K is at least 4, because if K is odd, we have the element 0, 1, -1, 0 in gamma. And so f of s z needs to equal negative c. Sorry, not this element. We have, well, -1, 0, 0, -1 is in gamma. That's the one that whoops. That's the one that so we should really be in PSL, but we're in SL. But this acts trivially. So this negative f of negative z, negative identity times z, is supposed to be -1 to the k times f of z. That's no problem if k is even, because this is saying f of z is equal to negative f of z. If k is odd. Okay, so there's no so we only have even guys. The holomorphic Eisenstein series of weight k exist when k is 4 and 6 and so on. And so this exactly extends as a holomorphic function, even though it's an infinite series. Yes, this is in MK. So that's the exercise. The definition is this. The exercise is you do have the transformation property that's required, and you need to work out whether it's holomorphic at infinity, which you can do by working out a Fourier expansion. So that's another exercise in exactly the same way as we did for the other Eisenstein series, except instead of k-Bessel functions, you get much simpler things. So exactly, Fourier expansion. Yeah, exactly. There's a constant term of zeta of k and some divisor sum sigma k minus 1. Yeah, depending on zeta k to zeta k, something like this, and then a sum over non-zero q to the n with some constants that I'm sure. 2 pi's and gammas. Yeah. Good, you got it off the top of your head. Good. Yep. Good. So in particular, I wrote k not equal to 0, but I should have written k bigger than 1 because this is the constant term, and here's the power series. Okay. Anything else I want to say about this? Right. So here's another exercise. Again, it's not hard. So if we take, well, there's this whole graded ring of this is a graded ring of all weights, and the exercise is that E4 and E6 generate. In other words, if I take something of weight k and something of weight L and I multiply the two, I get something of weight k times L, exactly because of the multiplicative nature of the definition. So these generate this ring, and in particular, if we, let's see, I think the zeta of, I think actually the zeta is if I hadn't made this co-prime. So I did the co-prime thing. So this should be actually be 1 or 2 or something. Let's say it's 1. Let's say I put a 1/2 there so that this is a 1. The reason I want to do that is, and notice that if I take E4 cubed, then I get something of weight 12 with leading coefficient 1. And if I take E6 squared, then I also get something of weight 12 and leading coefficient 1. And so if I subtract off those two, I get something with leading coefficient 0. And of course, you know what that is. So notice this is in the space of cusp forms of weight k. So this is cusp forms. These are the ones. There's a variety of ways of. So cusp forms are when the 0th Fourier coefficient of f vanishes. What that really means, if you go back to this point of view, or rather, where is it? Yeah, okay. The point is that this sum goes from 0 to infinity. If you go back to this point of view, if the 0th coefficient is 0, then actually not only is it bounded everywhere, it actually goes to 0 at infinity. Okay, this is equivalent to f goes to 0 as y goes to infinity. Okay, so the modular form decays to 0 up in the cusp. Okay, right, and this function, well, if I've normalized things properly, which I'm sure I haven't, but you can work out what, so this is going to be some constant times what's called the Ramanujan discriminant function. This is Ramanujan discriminant.
Oh.
I think I need a 1 over 1728.
Yeah.
Sorry, over here I need a 1 over 7. So here it's going to be a 1728. But who cares about constants? Is a Ramanujan discriminant function, which is given alternatively by the following the following Q series, well, Q product, and so on. Then you can work out what this is. So the leading term, of course, is Q if we take all ones. If we want to get a Q squared term, well, the only way we get a Q squared term, all of these are going to have higher order. So the only way we get a Q squared term is if we take all ones. And here, when we open this up by the binomial theorem, the first thing we get is a minus 24. So we get a minus 24 Q squared, and then higher order terms. So if we write this as a sum tau of n, Q to the n, this is the famous, and n starts, of course, at 1, since tau of 0 is 0. We always have this Q. This is the Ramanujan tau function. Tau function. I didn't prove it.
Okay.
I didn't prove it. There's a variety of ways of seeing this. My favorite is through Euler's pentagonal theorem. Let me say use Euler pentagonal theorem, or a standard proof is the Jacobi triple product formula. Jacobi triple product. So really, this is the 24th power of the eta function. And the eta is 1 over eta is related to the partition function. So yeah, okay. The generating series for the partition function. This all goes back to Euler in some sense. Generating series for the partition function is something like if I take 1 over this and this and this and so on. Euler observed, well, what is this? This means 1 over 1 minus q, I know as 1 plus q squared plus q cubed and so on. And then 1 over 1 minus q squared is 1 plus q squared plus q to the 4 plus q to the 6 and so on. And you multiply all these out, and when you get a coefficient, so this is a sum, it turns out the partition function 0. There is a constant term here. So this is the partition function. So for example, what's the coefficient of q cubed? Well, I can get a q cubed either from here and then all ones, or from here and then all ones. And there's also a q cubed leading term, yes, in the next thing. Thank you. Or from here. And that corresponds to the partitions of 3 as just 3, that's this, or the partition of 3 as 2 plus 1, so that's this, is 2 plus 1, or the partition of 3 as 1 plus 1 plus 1, and that's this.
Sure. So the first term is how many ones, how many
Yep,
twos.
how many ones, how many twos, how many threes, and so on. And when you collect that, that exactly gives you, so the number of occurrences of q cubed will tell you the partition. Okay, so that's what Euler was interested in, and it's a hop, skip, and jump from that to eta. You need this q to the 1/24th, and then when you raise things to the 24th power, you get delta. All right. Again, I'm trying to get the Hecke operators. So the important thing about cusp forms is that they are, so if f in sk, so this is a cusp form of weight k, And it has a Fourier expansion, f of z, a q expansion, a sum over n bigger than 1 of af of n q to the n, we can form an L function. So this is usually called the Hecke L-function. Although you'll see it's basically it's the Riemann L-function following Riemann memoir. Just do the same thing, Riemann memoir, just do the same thing as what Riemann did with theta functions. Hecke observed you could do this in general for a modular. Do for a modular form, when we made this theta function, we took the theta function along the vertical axis. Okay, so we have f of iy. If we take this same Mellin transform of the function y to the s dy over y, right? There's one thing. Okay, I'll come back to that. Let's work out what this is. So I need to know whether I can interchange integrals and summation here, but let's set that aside for 1 second. So if I just put in the series expansion, af of n e to the 2 pi I n z, but z is iy, so this is e to the minus 2 pi I n y, y to the s dy over y, summed over positive n. See, if I had n equals 0 here, then I'd be integrating af of 0 times y to the s from minus infinity to infinity, which would not converge. There's no value of s for which this polynomial, the polynomial either diverges at infinity or diverges at 0. So, the fact that I always have exponential decay tells me I can execute this integral. And we're going to do exactly the same thing. We'll reverse orders, n greater than 1, af of n, and then this integral from 0 to infinity, e to the minus 2 pi n y, y to the s dy over y. And now we do the familiar thing, replace y by y over 2 pi n. I think I can just do this directly, and 2 pi n to the s. And what's left is yep, I just made that change of variables, pulled that out. So we're left with,
now we're left with gamma.
now we're left with gamma. Okay, so this is a very simple way to get to the completed L function of f, which is, I guess, 2 pi to the s, gamma of s, and then the L function, where the L function is equal to the same coefficients. This is just a process by which you take, where was it? Here, you take the Fourier coefficients and turn them into Dirichlet coefficients. Okay, so this Mellin transform converts Fourier coefficients, Fourier expansions, or Fourier coefficients. Let's call them expansions. Nothing's happening to the coefficients. Expansions into Dirichlet series. Dirichlet series with the same coefficients. Okay, was I allowed to do this? In what ranges of S was any of this valid? Yes. So this was q to the n. Q, if you recall, is e to the.
Just remember the change variables.
Yes.
So basically, 2 pi should be 2 pi and the s minus 1.
Dy over y. Dy over y is Haar measure.
Right.
So it's invariant under this.
Sure. Okay. Right.
So all that happens is.
Only y to the s happens. Okay. And why do we have 2 pi to the s in front of it? Should be 2 pi to the minus s in the last step for like.
Yes, thank you. The 2 pi is in the denominator. Thanks.
Okay, that's not as much.
Beautiful. Okay. Was any of this justified, and in what range was it justified? So we need bounds on these Fourier coefficients.
Sure, okay.
Okay, yep, let's do the Hecke. Hecke would not be so happy that this is now indeed called the trivial bound. The trivial bound on these Fourier coefficients. So, so the key idea here is to observe that if you take f of z, that changes by multiplying by cz plus d to the k. But if I multiply this by imaginary part of z to the k over 2, that also changes, but by 1 over absolute value of cz plus d to the 2k over 2. So if I take absolute values, this function is automorphic. This is automorphic. And so it's whatever values it takes in the fundamental domain is what it takes everywhere. And as I go to infinity, remember that this decays exponentially. This decays exponentially. Whereas this is at infinity polynomial growth. Polynomial growth. So this goes to 0 at infinity as you go up in the cusp. The product goes to 0, which just means, well, there's some compact part and then it goes to 0. So it's just bounded universally. This means this thing is just bounded by a constant independent of z. So for all z in H, we have this bound. That's why it's the trivial bound. That's the only observation. What this tells us is, well, what if we integrate 0, 1, f of x plus iy? I want the nth Fourier coefficient. So I guess I'll multiply by e to the minus nx dx. That's almost the nth Fourier coefficient. It's the nth Fourier coefficient times the y part. Yeah, let me just artificially stick in a y to the k over 2 on both sides. The integral is in x, so that's just a constant as far as dx is concerned. And then I pick off I've integrated out the e to the minus 2 pi, e to the plus 2 pi nx against e to the minus 2 pi nx, but I still pick up the e to the minus 2 pi ny. So this is just a universal identity. Exactly, let's put absolute values on everything. And let's bound by the triangle inequality. I'll pull this sum inside. So I have now f of x plus iy, y to the k over 2. This has absolute value 1, integrated dx. This thing, as we just said, is bounded by a constant, integrated from 0 to 1. So this is just bounded by this constant, c. Of course, c can depend on f. Okay.
It should be c times an x. I don't know. That's
right. So this looks bad. This looks very bad. This looks like what we've shown is that AF of n is bounded by some constant times e to the 2 pi ny times some y to the k over 2. So this is exponential growth. That means this L function is not convergent anywhere. This is, yes, exactly. It's true for all y. So before we make that observation, L of wouldn't converge anywhere. Wouldn't converge anywhere. But exactly as you said, but this is true for all y. And so we can set y to be 1 over. Okay, and when we set y to be us, this should be a y to the minus k over 2, since there was a y to the k over 2 when I brought it to the other side. Okay, so that makes this a constant, and that makes this n to the k over 2. Okay, so the Fourier coefficients are bounded by n to the k over 2, which means the Dirichlet series converges So this was all okay. Sorry, let me slow down a little. So far, so good. So this was all okay if this was all okay if the real part of S is bigger than, what is it, K over 2 plus 1 or something. I guess K over 2. That's one. Whatever, it doesn't really matter. As long as the real part of S is sufficiently large. Okay, so then all of these interchanges were just fine. We have to be, well, what we want for this to be an L function is for it to have analytic continuation. What about analytic continuation? What about analytic continuation? By the way, what's the truth about the growth rate?
Minus a half.
Yeah, exactly. So Deligne tells us that actually, and Ramanujan conjecture, this is the Ramanujan conjecture, this is less than not just n to the k over 2, but k over 2 minus a half. That's true for primes, and then I'll put a plus epsilon for general numbers. Okay, this was the Ramanujan conjecture. Okay, what about analytic continuation? Well, exactly as Riemann did. We had this integral from 0 to infinity of whatever, right here. I'll break that into an integral from, actually, let's break it from, let's say, I don't know, alpha to infinity plus 0 to alpha. From alpha to infinity, since we're not reaching near 0, f from alpha to infinity is going to be an entire function. This is entire. This is already entire. From 0 to alpha, okay, let's work through this. I have f of I y, y to the s, dy over y. Yeah. Okay, so this is not my favorite normalization. This is not my favorite way to do things. Let's switch to my favorite way to do things.
Okay.
Because of this growth rate, I want coefficients that grow like n to the epsilon, not n to the k over 2, k minus 1 over 2, the epsilon. So a slight fudging will be, let's call them alpha f of n, be the AF of n's, but divided by n to the k minus 1 over 2. So then Deligne's theorem is that the alpha fn's are like n to the epsilon. And then if I make L functions, so I'll redefine new definition, the L function of fs, I want to be a sum over these alpha fn's over n to the s. So to put it back into the original framework, it's AF of n over n to the k plus 1 over 2, k minus 1 over 2 rather. So it's just a little shift. And the way to make that little shift happen inside the, so now I want to consider the integral from 0 to infinity f of Iy, not y to the s, but y to the s plus k minus 1 over 2, dy over 1. Everything else will be the same. The same argument as before will give us now this version of the L function, there's going to be a 2 pi to the minus, not s, but minus s minus k minus 1 over 2, and a gamma not of s, but of s plus k minus 1 over 2. So this is what I'll call the completed L function of s. It's ever so slow. This is the automorphic normalization, as opposed to the modular normalization. A lot of things become much simpler if you use these alphas instead of the actual Fourier covariates. In other words, when I write the Fourier expansion, we'll now read f of z is equal to a sum over n instead of A, I'll have alpha f of n times n to the k minus 1 over 2 q to the n. Okay, so just a very slight renormalization of everything. Okay. Yeah, so now let's go to this integral. So this is also equal to an integral from we said alpha to infinity plus 0 to alpha f of iy. Now I have my nice normalization f y to the s plus k minus 1 over 2 dy over y. I haven't done anything yet. Following Riemann, I'll send y to 1 over y. As I said, this is just Riemann repackaged. Now I have an integral. So the change of variables gets a minus sign. The minus sign lets us reverse these orders from 1 over alpha up to infinity, f of I over y, y to the minus s minus k minus 1 over 2 dy over y. Okay, but f of I over y is also equal to f of 1 over negative 1 over iy, which is f of s acting on iy, where s is my favorite 0, 1, negative 1, 0. But by modularity, this is equal to c. C is, let me put the minus sign there. C is iy, cz plus d, d is 0, to the k, f of z. Well, z is iy. Okay, so this whole thing becomes an integral from 1 over alpha to infinity, f of iy, an I to the k out front. I to the k is either plus 1 or minus 1 because k is even. And a y to the k, which I'll write as y to the, there's a minus k over 2 and a y to the k, so that's a k to the plus over 2. There's a plus 1, and I want to write that as a minus a half. So I want to have a plus k minus 1 over 2, and I claim that the way to do that is to put a 1 minus s here. dy over y. You see why that normalization is very nice. Okay, so two observations. One, so let's go back to the, so this is also entire in S. This is also entire in S. So now we have a sum of two things entire in S. So let's observe, we've replaced, so remark, instead of Poisson summation for theta functions, we replace that with modularity. Use modularity. In other words, we've assumed Poisson summation in some sense. We assumed f was modular. That's what gave us this, this exactly same procedure. Okay, this is entire in S, which we can observe for any finite alpha. And now as I send alpha to, I guess, infinity, the first integral does nothing. 1 over alpha goes to 0. And I get the same integral, except with this factor I to the k, and the same integral for f, but now at 1 minus s instead of s. So I get the functional equation and the holomorphic analytic continuation. So far, so good.
So the Hecke L-functions, the functional equation had
Gauss
minus 1 or something like that.
Yep.
Now we have
Exactly. And of course, you can do this in level, and you can do this in much greater generality. And there's a way to do this representation theoretically, analytically, and so on. There's a lot more that I'm leaving off. So here's we want to talk about Hecke operators, and we're going to do that right now. So should we consider these L functions? These L functions, they come from modular forms. They have functional equations, analytic continuation. Not yet. There's one more thing that defines an L function. Starts with E, ends with product. Yeah. So in general, well, if you make H into some combination of F and G, if F and G are two Cusp forms, the space of Cusp forms is still a vector space, right? If this is a fixed weight. Of a fixed weight, for weight K, we have just a vector space, right? So if the dimension of this is more than one, I can take up my favorite linear combination, and then the L function for H will be that same linear combination of L functions of F and G. But by choosing alpha and beta, I can make this have zeros in the region of absolute convergence. Can be zero, not just off the line, but in the region of absolute convergence. You know, I can make a zero at S equals 100K or something. Like this would be very, very, very bad. This is not what L functions are. Exactly. Exactly. And Ramanujan actually conjectured this, amazingly. I mean, in the special case of delta, but we can be generous. Ramanujan conjectured that there was an Euler product, and Mordell proved this. And Mordell proved this in, I think Ramanujan conjectured this when he was looking at delta in 1917. Mordell proved this almost immediately, but it took, so it would be extremely anachronistic to say Mordell proved this in 1918 using Hecke operators, which were developed in the 30s. In the 30s, he develops the theory of Hecke operators, but it's really a generalization of what Mordell did in the case where the discriminant function, so fact, the dimension of the space of weight 12. Okay, so here's an oral question. What's the dimension of the space of weight 12 Cusp forms? Right. Which it's so in another general, I don't know, exercise fact, this is a simple thing. The dimension of the Cusp forms is always the dimension of the modular forms minus 1. So there's, yeah, and you can work out what the dimension of, yeah, so the dimension of weight 12, you have e to the 4, E4 cubed, and you have E6 squared. So of course you can arrange for their difference to be a Cusp form. So the weight 12 modular forms at dimension 2, the weight 12 Cusp forms at dimension 1. And so the discriminant function, well, it's alone. And so it's going to be any operator that you have on that space is going to be an eigenfunction of that operator because there's nowhere else to go. Okay, so that's kind of the distinction between what Mordell proved and what Hecke proved more generally about these operators. Okay, so let's get to these operators. Right, so the quotient H mod gamma is also the space of lattices, space of unimodular lattices. Right, because we can take one, if I want to make a lattice, I'll make one of the base points 1, and the other base point will be some traditionally called tau. Okay, I'll call it Z, not to confuse. And then we can put Z in the fundamental domain, and here's the square lattice, and here's the hexagonal lattice, and so on. So this is the space of unimodular lattices. Now you might think, what about not unimodular, but lattices of volume n? So index n, what about index n sublattices? What about index n sublattices? or lattices of covolume 1, which are how do they decompose and so on. So in other words, i.e., what we really want to ask about is, let's call it gamma n. This is the set of matrices A, B, C, D in M2 of Z with determinant not 1, but determinant n. So you can think of these as vectors, parallelepipeds of determinant n. Well, so what do we know about this space? There's an action of SL2Z on this space, because if I take anything here and I multiply it, in fact, I want to use little ABCD for elements of gamma. So let me call these capital ABCD. Capital A. Now that we're not doing quadratic forms, there shouldn't be confusion. So if I have something of determinant 1, I multiply it by something if I have something determinant n, I multiply by something determinant 1, that still has determinant n. So this acts on it. And so we'd like to understand the coset representatives. So what is the coset space? Well, if I have gamma in here, so if I have ABCD acting on some matrix of determinant n, ABCD, this is a big C, what do I get? Well, first thing I can do is notice that in the bottom left, I get AC plus CD. And by choosing, now I know that I know that AC together is not the 0 vector. Why not? Then the determinant is 0, and I'm looking at not index 0, not lattices of not full rank. Okay, so they're not both 0, which means by a choice of C and D, now they might have factors in common. I don't know. Regardless of whether they have factors in common or not, I can choose coprime C and D to make this linear combination 0. Divide out by the GCD, and then just match it. So there exists coprime C and D to make this thing equal to 0. But if that's the case, and this is going to be an integer 2x2 matrix with determinant 1, that means I have some, I have determinant n, thank you. That means I have some alpha and delta, where alpha times delta is equal to n. And then I don't know what's happening here. Let's call this beta. I've determined the bottom row of this matrix, but I have not determined the top row. Any matrices with the same bottom row differ by an element of exactly gamma infinity. Let me now call this n 1L01. And so what happens when I act on this by 1L01? Of course, I get the alpha and delta don't change, but beta turns into beta plus L delta, which means I can reduce beta mod delta. I can shift beta by multiples of delta. And beta is mod delta. And that's it. That's the coset space. So I don't know, let's call this lemma. A complete set of coset representatives is the set of matrices alpha, delta, beta, where alpha times delta is n, and beta runs mod delta. I wanted to say one other thing. Notice what we're doing. Notice what we're doing here when we set y to be 1 over n. We're actually integrating f of x plus I over n. We're integrating over this low-lying horocycle. This is at height 1 over n. So we're actually using some information in some sense. I mean, I would just want to plant that seed. We're about to look at what Hecke operators do. Right, so what's a Hecke operator? So let's define a slash operator. I really need to step on the gas. a slash operator of weight k of C. There's a variety of ways of defining this. Yeah, fine. Let me put the determinant in. Determinant to the k over 2, cz plus d to the negative k, f of z. Okay, a convenient.
I can look at the proofs of the computation of Hecke operators, and I can look at, like, I can look at the proofs of things that are eigenfunctions of operators. Like, I know where to find all of those.
Yeah, it's good to record them too. I think there's some treatments that are better than others.
Okay.
So it's okay. Well, let's just keep going. Anyway, we started a little late.
So I guess I was going to say, for press for time, maybe getting more the picture of the point. Would be more useful than seeing probability computation.
Great.
When I know how to find it.
Great.
That's it.
Yep, absolutely. So so you could say f is in Sk if and only if for all gamma in gamma, f is an eigenfunction of the slash operator. And of course is holomorphic and so on. So what we'll do is we'll make a Hecke operator, Tnf, which is quite simply this. You sum over these coset representatives, f slash gamma. Now, the main exercise here, this is not entirely trivial. The main exercise is that Tnf, if f is in Sk, implies that Tnf is also in Sk. So this is not trivial because if you look at how this action, so by the way, well, it is an action, first of all. So a little exercise is that f slash gamma 1, gamma 2, where here's multiplication, is f slash, I mean, yeah, it's not hard to see, f slash gamma 1 slash gamma 2. So what's happening here is that let me not take the time to do it, but that these, when you apply an element of SL2Z, it permutes. So this exercise is that an element of SL2Z applied with the slash operator, slashing with element of SL2Z, permutes the coset representatives, the cosets. So this is important if you haven't seen this before, that this permutes these cosets, and that's why you get something that's at the end invariant. In general, you've taken some linear combination. These gamma n's are not in your group. So f is not invariant under gamma n. It's only invariant under gamma. But because you've taken this set of coset representatives, in fact, it will, when you slash with an element of SL2Z, you will still get something. You'll be invariant because you'll still be summing over the cosets in some permutation. So that's the importance of this exercise. And another exercise is that if you apply Tn and then you apply Tm as an operator, that's the same. Now this takes a little bit more work. It's the same as summing over the divisors as d dividing mn t of n. So d divides n and d divides, sorry, d dividing n and d dividing m of Tm over d squared. Did I get that right? I think I got that right. Yeah, well, yeah, exactly. If it divides both of them, then it divides their GCD, and so I can form this quotient. Okay. In particular, this side is obviously invariant under replacing n and m, and so is this side. So this implies that these operators commute. We also have the Petersson inner product. So the space SK has natural structure as a Hilbert space. Hilbert space structure with respect to the Petersson inner product, which is just the sort of obvious thing. You take f of z, g of z bar, dx dy over y squared, integrated over the fundamental domain, h mod gamma. The only problem is this function, f times g bar, is not automorphic. F changes by, so I can't write here this quotient. F changes by cz plus d to the k. G changes by cz plus d to the k, and I put a bar. So I have absolute value cz plus d to the 2k. But if I multiply by y to the k, that changes by absolute value of cz plus d to the 2k in the denominator. So that exactly, so this thing is automorphic. If f and g have, of course, weight k. Okay, so using still holomorphic functions, we can make something automorphic by sticking in this imaginary part. Well, we have a bar, and then we have this imaginary part. So this is the inner product of f and g, the Petersson inner product. And another exercise is that the TNs are self-adjoint. TNs are self-adjoint. So again, if I apply it to f, or I apply it to g, these two things are the same, and you open up what this is and move it piece by piece to the other side, and again you'll recover some that there's a permutation on the elements. It's not entirely trivial, but it's a simple enough exercise. Right. So what is TF, by the way? What is this? We didn't actually write it out. So we know what the coset representatives are. It's this thing. So this is a sum over alpha times delta equals n, and a sum over beta mod d mod delta of f slash this matrix. So the determinant of that matrix is always n to the k over 2. C in all those matrices is 0, so I get d to the minus k. Now n is alpha delta. So I get alpha to the k over 2, delta to the k over 2, delta to the minus k. So this is actually alpha over delta to the k over 2. Combining all of these things. And then f of alpha z plus beta over delta. Just cz plus d. Az plus b over cz plus d. Okay, so that's what this operator is. Now let's think about this for a second. I want to make this point. Example. Let's look at TP, TPF. Where is this being sampled? So it's a sum over the possible divisors of P, which are 1 and P. So either A is equal to 1 and D is equal to, let's say A is equal to P and D is equal to 1. Then the B sum is mod 1, so there's only a single contribution. This, when B is 1, and so I get a P to the K over 2. P to the K over 2 times F of PZ. The other option is that A is equal to 1, D is equal to P, and then B ranges mod D. And now A is 1, D is P, so I get P to the minus K over 2, P to the minus K over 2, and then F of alpha, alpha is 1, so I get Z plus B over D. Z plus B over D, D is P. So look at where we're sampling these points. We get a single contribution at height P. If Z is wherever Z is, let's say Z is here. So now I multiply Z by P, wherever that is, and then I can move it back into here. So PZ is somewhere there. Or I take Z and I divide it by P. If P is large, that's somewhere here. And then I shift by B over P, summing over all shifts. it's also a low-lying horocycle. Just like when we picked off the Fourier coefficients. That's not going to be an accident. Okay, this is also a low-lying horocycle. I mean, it's a discrete one, as opposed to a continuous one. Okay, right. Yeah, yeah, because this B ranges mod D, D is P. So it's this combination. This is a weird thing to do to a function. To take this combination of things with these coefficients. Here there's P things in the sum. Here there's only one contribution. But that this combination is, if F is invariant under the slash operator, then that combination is also invariant under the slash operator. So everybody moves around. That's what I meant by this exercise, this permutation of the cosets when you act with the game. It's a really good exercise to do. I strongly encourage it. Okay, right, good. So the last thing to do is to say, okay, we have a family, an infinite family of self-adjoint commuting eigenfunctions on a finite dimensional vector space. So there's if it's self-adjoint, then I can get eigenvalues, then I can diagonalize. Self-adjoint means like the operator is transpose invariant. So if it's symmetric, then it's diagonalizable. And if they all commute, then we can simultaneously diagonalize all of them. So commuting and self-adjoint, this is linear algebra, adjoint on a finite dimensional vector space, implies there exists a basis of simultaneous eigenfunctions. One of the best theorems ever. Yeah, I learned this theorem from John Conway, freshman fall linear algebra. And the way that he demonstrated it was he brought in a coat hanger, and he took this coat hanger and he held it upside down, so it looked like this. And then he pulled it into a diamond shape, just pulled this up to make a diamond shape. And then he balanced the penny here. And then he started the whole thing spinning on his finger. So imagine like a diamond, and he puts he's holding the coat hanger on his finger, balances a penny, and starts the whole thing spinning. And the penny stays on the tip. And once he's diagonalized this, he's going to commute that with taking an umbrella and balancing it on his chin. He's just showing off, obviously. But so I will never forget that commuting operators can be simultaneously diagonalized. Once you've got this thing spinning, there's nothing stopping you from taking the umbrella and balancing it on your chin. And then, of course, he takes the umbrella off, and then he stops it, and the penny's still on the coat hanger. I will never forget this theorem. Commuting I do not have those. I worked actually, after I saw that lecture, I spent the weekend. My poor roommate, pennies kept flying at his head as I worked on the coat hanger trick, and I eventually got it. I could probably do it again with some practice. It's been 20 years. Okay, all right. So between the two of us, we can repeat Conway's. A basis of simultaneous eigenfunctions, and then there's a really nice calculation. I don't think it takes too long. I think we can actually do it. So let's say f is an eigenfunction of all the Hecke operators. So this is called a Hecke function, Hecke eigenfunction. So in the case of the discriminant function, it's automatically an eigenfunction of all the Hecke operators because they keep you in S12, and S12 is a one-dimensional space. Do any of the Hecke operators kill the discriminant function? No one does. Unknown. Lamer's conjecture is that they don't. Lamer conjecture is that they don't. Well, the Lamer conjecture is that tau of n is never 0.
Oh, okay.
And the tau of n's, we're about to see that the Fourier coefficients are the eigenvalues, right? So if the Fourier coefficients are the eigenvalues, and well, if you kill the guy, then your eigenvalue is 0, then tau is 0. So the tau is non-vanishing, is exactly this conjecture. Okay, say we have an eigenfunction. So what does that mean? That means that Tnf is lambda n f. And on one hand, we have this Fourier expansion, lambda n sum over, I have to use some letter like L. It's a Cusp form, so I start at 1. There's my Q series. On the other hand, this is equal to the whole shebang. So let's write out what that is. It's a sum over AD equals N and a sum over B mod D. And then what do we have? A over D to the K over 2? F of AZ plus B over D? I think that's right. Yeah, that's right. Okay, but this, of course, we can write out as in its Fourier expansion. So let's sum over, let's say R bigger than 1. And I have, oh, and the whole point of using these alphas is to put an L to the K minus 1 over 2. Because the coefficients themselves are actually A's, and I prefer alphas, as you'll see. And then here again, I get alpha f of r to the k minus 1 over 2. And then e to the 2 pi I, q to the r. Okay, let me write this out. E to the 2 pi I r z, but z is az plus b over d. Technology is beautiful. AZ plus B over D. Okay, great. So let me just move this down here. AZ is N, B mod D. So far, so good. I haven't done anything. On one hand, this. Sorry, say it again. Oh, thank you. A over D to the K over 2. Thank you very much. Okay. So what happens to the D sum? Because the only place where I see a B is over there. Over a complete. Yeah, we have a complete sum. Oh, it is 0 unless R over D is already an integer. Yeah. So this is 0 unless R over, in other words, unless D divides R. And if D divides R, then you're summing 1 D times. So you get D if D divides R and 0 otherwise.
That makes more sense. Some numbers.
Yep, it is 0. Yep. So, so if that's the case, then the only R's, let me put it another way, if the D is here, the only R's that occur are those that are 0 mod D. So let me replace, okay, let's do this in 2 steps instead of doing it all at once. I have my A over D to the K over 2. The D sum now comes out with a factor, the B sum rather gives me a factor of D. And let me change R to R times D. So I get an alpha F of R times D, R times D to the K minus 1 over 2, and an E to the 2 pi I R times D over D. So that's just R A Z.
I see. Okay. Sorry.
Okay.
So we just replace the reindex.
Yep, reindex. Okay. The only R's that occur are those that are multiples of D. So let me reindex. Okay, so this was under R goes to R times D. And now let's call RA L. Okay, so this is a sum over L. Now I have a Q to the L. Now I have a nice Q to the L. Q to the L. Okay. A is a divisor of L. So I have a sum over A, which is a divisor of L. A is also a divisor of N. AD divides N. A over D to the K over 2, D. And then what is R? R times D. Yeah, so this is alpha F of R times D. If L is equal to R times A, then R is equal to L over A. And R times D, well, is just LD over A. And then I have an R times D, which is an LD L times D over A to the power K minus 1 over 2. Okay. Yeah. Oh, I'm sorry, not divides N. That's A divides N. But I want to keep track of what the other, what N over A is. I'll call that X. Okay. But look at this. This is a Q series. And this is the coefficient in front of Q to the L. And this is a Q series. And this is the coefficient in front of Q to the L. So those two things must be the same. So for all L, I have that lambda of N, AF of alpha F of L, L to the K minus 1 over 2. That's on this side, is equal to everything over here. So let's clean this up a little. I have a sum over A dividing L, A times D being equal to N. Can I clean this up? Well, first let me put the alpha F of L times D over A. What power of A do I get? I have an A to the K over 2, and here an A to the K over 2. Don't this K and this K over 2 cancel? And I just get a 1/2, A to the 1/2 in the denominator. A to the minus a half in the denominator is an A to the 1/2.
Yeah, I agree.
Okay. How about D? Here's a D to the K over 2 minus 1. Here's a D to the K over 2 minus a half. Yeah, so the K over 2 and the K over 2, this is the denominator. K over 2 cancels that K over 2. This is a D, and that's a D to the 1, and this is a D to the minus a half. So I think I get D to the 1/2. You buy that?
Yes.
And then I get an L to the K minus 1 over 2. Okay. So this is actually nice and clean. The L to the K minus 1 over 2 is cancel. I get a lambda of N. Oh, yeah, that's right. Lambda of N, A F of L. Now, what about A times D? N to the half. A sum over A dividing L, a sum over A times D being equal to N of the L times D over 8th coefficient. All right, some quick corollaries. We're out of time. Corollaries. If L and N are actually coprime, then what do I get on this side? A divides L and A divides N. So A must be 1. I get that L of N alpha F of L is equal to N to the half. And then if A is 1, there's only one contribution, which is when D is N. So I get an alpha F of L times N. Okay, so that's 1. Part 2, what if L is equal to 1? If L is equal to 1, let me read this formula. So now I have lambda of N times alpha F of 1 is equal to N to the half alpha F of N. So what that means is if alpha F of 1 is 0, if this number is 0, then all of these numbers are 0. Then alpha F of N is 0 for all N, which means that F is 0. All the Fourier coefficients vanish. Or alpha F of 1 is non-zero, in which case we can rescale F to be what's called Hecke normalized, unlike L2 normalized. There's a fun thing there. Rescale F to be Hecke normalized, and by which I mean set alpha F of 1 to be 1. Then, again, reading this formula, if you rescale alpha 1 to be 1, just by dividing out whatever its value originally was, then we get that the eigenvalues are exactly, I guess, lambda n over root n is exactly alpha F of n. Okay.
So alpha F of 1 is the Fourier coefficient of the Q term.
The Q term, yeah. So make the Q term, make the coefficient in front of the Q term 1.
Right. Sometimes the coefficient of the Q term is 0. They can make non-trivial Cusp forms which manage the second order.
So
like delta squared.
Delta squared will not be an eigenfunction of all of the Hecke operators.
Oh, so that's the conclusion. Is that if it vanishes to second order, then it's not an eigenfunction of Hecke.
Right?
Sure. Okay.
So here's a really fun exercise. You're absolutely right. Well, delta squared is in S24, which means it's some combination of the things in S24. What combination is it? S24 will be given in terms of some powers of the 4 and 6 Eisenstein series.
Sure. So I can write down normal thing for delta in 4 and 6 and then square that.
Yep. So expand, what is this? What is this in terms of E4 and E6?
So sure, E4 to the
well, now you have a lot more combinations. You want to know how many ways is 24 written as a sum of 4s and 6s? So E4 times, what is it? E4 times E6 times E4 times E6 times E4 is also 24 as weight total, right? 4 plus 6 is 10. So you add another 10 and you add 4 more, you get to 24. So there's a lot more combinations, but you just work out the first couple of coefficients of all of those things, and then it's linear algebra to work out what the decomposition is. It's a fun exercise. Anyway, the point is this is not an eigenfunction. So what you just proved is that this is not an eigenfunction of all Tn, because if it were, it would violate this this principle. Okay, let's see. What can I say in on 1 foot? Right, and let's go back here. Now that we know that lambda n, it was the nth Fourier coefficient. So let's put that back in. So another corollary. I'll put back in what I know about lambda n. So now assume f is Hecke normalized. Assume f is Hecke normalized. Then this lambda n times a alpha L is actually n to the half alpha n times alpha L. And the n to the halves on both sides cancel. And I get exactly that if n and L are co-prime, then alpha Fn times alpha Fl is alpha F of n times L. So this is this multiplicativity.
That's how you get the of Ramanujan L-function.
Exactly.
Okay.
Exactly. It's not complete multiplicativity. So
Right. I don't know.
on relatively prime things. Right. And all right, I'm really out of time, but what can I say? Well, the most important thing to say is to finish the L function. So let's finish the L function. When you read this formula, so now all we care about is powers of primes. Okay, let's read this formula when, copy and paste this formula. And we'll read it. Okay, so corollary, another corollary. Corollary is that for n equals p and L equals p to the r, what happens to this formula? I have n is equal to p. L is p to the r. What divisors are there of p and p to the r? 1 and p, exactly. So I get, yeah, and this lambda p we already know is p to the half alpha of p. So the p to the halves cancel on both sides. So we have this formula that alpha of p times alpha of p to the r is a sum of two things. When a is equal to 1, d is equal to p. Oh, and that's the p to the r. Somehow I lost the L. So I get alpha of p to the r plus 1. I get the second order recursion relation. Plus alpha of when a is equal to p and d is equal to 1, then I get p to the r minus 1, p to the r minus 1. Okay, so when you write your L function, so L F S being a sum of these alpha Fn's over n to the s. Yes, because this is the eigenvalue. Yes, let me rewrite it here. Alpha f of p times alpha f of p to the r. So this thing is a product over all primes. By multiplicativity, I can decompose this into prime powers. I have 1 plus alpha f of p over p to the s plus alpha f, I don't know what p squared is, over p to the 2s, and so on. But by this second order recursion relation, you will learn that this is equal to a product over primes. So exercise using star, exercise from star, is that this is equal to 1 minus alpha f of p over p plus 1 over p to the 2s inverse. In other words, if I take this thing and I multiply by all of these, then I get this alpha p multiplying each of the terms, which gives me this cascading thing. Okay, so that's it. That now we've given our Euler factor, our Euler product. And in fact, if we factor this further, so this is a quadratic polynomial in p to the s. So we factor this, oh, I can't call it alpha. Alpha is really the right name for the Satake parameters. Give me another letter. Delta, eta, fine, eta. Oh God, such a bad letter. Theta. Yeah. Okay, I'll call it theta. Theta of p over p to the s inverse, and 1 minus, I don't know, beta of p over p to the s inverse. In other words, I'm just factoring this quadratic polynomial, 1 minus alpha of p x plus x squared as x minus theta times x minus beta. So if you just factor this polynomial, or I guess I'm writing it as 1 minus this, theta x and 1 minus beta x. So then theta times beta has to be 1. Theta of p times beta of p has to be 1. And theta of p plus and theta of p plus beta of p has to be alpha. So you have two numbers whose product is 1 and whose sum is alpha. I think the minus signs will exactly match. So one of two things happens. Either theta and beta are real, and in which case this is a hyperbola, right? I have x times y equals 1, and then x plus y will be restricted to that hyperbola, will be like a hyperbolic cosine. So that means that alpha is greater than 2. Or the only other option is that theta is equal to beta bar, and they have absolute value 1, in which case theta plus beta adds up to no more than 2, which is the absolute value of alpha. And so Deligne shows that it's this. That's the Ramanujan conjecture. This is why it's the Riemann hypothesis. Your possible values for theta and beta are to be on the real line. Maybe theta is here and beta is here, so that their product is 1. Or theta is here and beta is its complex conjugate. They're on the unit circle. So Deligne is proving the Riemann hypothesis that they're on this line. They're not these roots are not off of this line. This is the Riemann hypothesis for varieties. And so yeah, maybe we'll stop there.